हेलो फ्रेंड्स, तो राना एकेडमी में आपका स्वागत है। हमने स्टार्ट किया 11th क्लास की एनसीईआरटी वन शॉर्ट सीरीज केमिस्ट्री की, जिसमें हमने 9th यूनिट तक कंप्लीट किया है। अब हम स्टार्ट करने जा रहे हैं 10th यूनिट, जो कि है हमारा द एस ब्लॉक एलिमेंट्स। द फर्स्ट एलिमेंट ऑफ अल्कली एंड अल्कलाइन अर्थ मेटल्स differs in many respects from the other members of the group. The S block elements of the periodic table are those in which the last electron enters the outermost s orbital. As the s orbital can accommodate only two electrons. Two groups 1 and 2 belong to the S block of the periodic table. Group 1 of the periodic table consists of the elements lithium, sodium, potassium, rubidium, cesium, and francium. They are collectively known as alkali metals. Reaction with water, which are strongly alkaline in nature. The elements of group 2 include beryllium, magnesium, calcium, strontium, barium, and radium. These elements are alkaline earth metals. These are so called because their oxides and hydroxides are alkaline in nature, and these metal oxides are found in the earth crust. Among the alkali metals, sodium and potassium are abundant, and lithium and rubidium and cesium have much lower abundances. Table 10.1. Francium is highly radioactive. Its longest lived isotope, FR, has a half-life of only 21 minutes. Of the alkaline earth metals, calcium and magnesium rank 5th and 6th in abundance respectively in the earth crust. Strontium and barium have much lower abundance. Beryllium is rare, and radium is the rarest of all, comprising only 10 to the power minus 19 percent of igneous rocks. Table 10.2. The general electronic configuration of S block elements is noble gas NS1 for alkali metals and noble gas NS2 for alkaline earth metals. Lithium and beryllium, the first elements of group 1 and group 2, respectively exhibit some properties which are different from those of other members of the respective group. Now, in these anomalous properties, they resemble the second element of the following group. Thus, lithium shows similarities of magnesium and beryllium to be aluminium in many of their properties. This type of diagonal similarity is the as in is commonly referred to as a diagonal relationship, is due to the similarity in ionic sizes and or change radius ratio of the elements. Monovalent sodium and potassium ions and divalent magnesium and calcium ions are found in large proportions in biological fluids. These ions perform important biological functions such as maintenance of ion balance and nerve impulse induction. Group 1 elements, alkali metals. The alkali metals show regular trends in their physical and chemical properties with the increasing atomic number. The atomic, physical, and chemical properties of alkali metals are discussed below. Electronic configuration. All the alkali metals have one electron configuration NS1 outside the noble gas core. The loosely held s electron in the outermost valence shell of those elements makes them the most electropositive metals. They readily lose electron to give monovalent positive ion. Hence, they are never found in free state in nature. Atomic and ionic radii. The alkali metal found and the alkali metal atoms have a largest sizes in a particular period of the periodic table. With increase in atomic number, the atom becomes larger. The monovalent ions are smaller than the parent atom. The atomic and ionic radii of alkali metals increase on moving down a group, that is, The increase in size while going from lithium to cesium. Ionization enthalpy. The ionization enthalpies of the alkali metals are considerably low and decrease down the group from lithium to cesium. And this is because of the effect of increasing size outweight and increasing nuclear charge, and the outermost electron is very well screened, screened from the nuclear charge. Hydrogen enthalpy. The hydration enthalpies of alkali metals ions decreases with increases the ionic sizes. Lithium is greater than, sodium is greater than, potassium is greater than, rubidium is greater than cesium. Lithium has maximum degree of hydration, and for this reason, the lithium salts are mostly hydrated. LiCl plus LiCl dot 2 times H2O. Physical properties: all the alkali metals are silvery white, soft and light metals. Because of the large size, these elements have a low density, which increases down the group from lithium to cesium. However, potassium is lighter than sodium. The melting and boiling points of the alkali metals are low, indicating weak metallic bonding due to the presence of only a single valence electron on them. The alkali metals and their salts impart the characteristic color now to the oxidizing flame. This is because the heat from the flame excites the outermost orbital electron up to a higher energy level. When the excited electron comes back to the ground state, there is a emission of radiation in the visible region of the spectrum as given below. Alkali metals can therefore be detected by the respective flame tests and can be determined by flame photometry. Now, to atomic absorption spectroscopy, these elements, when indicated with light, the light the light energy absorbed may be sufficient to make an atom lose electron. This property makes cesium and potassium useful as electrodes in photoelectric cell. Chemical properties: the alkali metals are highly reactive due to their large size and low ionization enthalpy. The reactivity of these metals increases down the group. Reactivity towards air: the alkali metals tarnish and dry air due to the formation of these their oxides, which in turn react with the moisture to form hydroxides, and they burn vigorously in oxygen, forming oxides. Lithium forms monoxide, sodium forms peroxide, the other metals form superoxides. The superoxide O2 negative ion is stable only in the presence of large cations such as potassium, rubidium, cesium. In all these oxides, the oxidation state of the alkali metal is +1. Lithium shows exceptional behavior in reacting directly with nitrogen of the air to form the nitride Li2 Li3N as well. Because of their high reactivity towards air and water, alkali metals are normally kept in kerosene oil. Problem 10.1: what is the oxidation state of potassium in KO2 solution? The superoxides species is represented as O2 negative since the compound is neutral. Therefore, the oxidation state of potassium is +1. Reactivity towards water: the alkali metals react with water to form hydroxide and dihydrogen. It may be noted that although lithium has most negative negative value, table 10.1, its reaction with water is less vigorous than that of sodium, which has the least negative value among the alkali metals. This behavior of lithium is attributed to its small size and very high hydration energy. Other metals of the group react explosively with water. They also react with proton donors such as alcohol, gases, ammeter, and alkalines reactivity towards the dihydrogen. The alkali metals react with dihydrogen at about 673 Kelvin, lithium and 1073 Kelvin to form hydrides. All the alkali metal hydrides are ionic solids with high melting points or reactivity towards halogens. The alkali metals readily react vigorously with halogens to form ionic halides, M positive, X negative. However, lithium halides are somewhat covalent. It is because of the high polarization capability of lithium ion, the distortion of electron cloud of the anion by the cation is called polarization. The lithium Li positive ion is very small in size and has high tendency to distort electron cloud around the negative halide ion. Since anion is with large size can be easily distorted among halides, lithium iodide is the most covalent in nature. Reducing nature, the alkali metals are strong reducing agents, lithium being the most and sodium are least powerful. The standard electron potential, which measures the reducing power, represents the overall change. Now, problem 10.2. The electron of the for Cl2 for Cl negative is plus 1 0.36. For I2 I negative is plus 0.53. Now for Ag positive, per Ag is plus 0.79. Sodium positive plus upon sodium is minus 2 minus 2.71. And for lithium Li positive per Li is minus 3.04. Arrange the following ionic species in decreasing order of reducing strength. In order, lithium is greater than sodium is greater than iodine is greater than Ag is greater than chlorine. Solutions in liquid ammonia. The alkali metals dissolve in liquid ammonia, giving deep blue solutions which are conducting in nature. M in bracket M plus in bracket X plus Y and H3 then gives produce M in bracket NH3 X times plus E NH3 Y times negative. The blue color of the solution is due to the ammoniated electron which absorbs energy in the visible region of light and thus imparts blue color to the sodium solution. The solutions are paramagnetic and on standing slowly liberate hydrogen resulting in the formation of amide. Positive plus electron then plus NH2 then gives NH2 plus half NH2. And when in concentrated solution, the blue color changes to bronze color and becomes diamagnetic. Uses lithium metal is used to make useful alloys. For example, with lead on the to make white metal. Now bearings for motor engines. With aluminium to make aircraft parts, and with magnesium to make aircraft plates. It is used in intermolecular reactions. Lithium is also used to make electrochemical cells. Sodium is used to make sodium sodium per lead alloy and needed to make PbET2, PbET4 and PbM4. These organolead compounds were earlier used as additives of to petrol, but nowadays vehicles use lead-free petrol. Liquid sodium metal is used as a coolant uh, in fast breeder nuclear reactors. Potassium has a vital role in biological systems. Potassium chloride is used as a fertilizer. Potassium hydroxide is used as a manufacture of soft soap. It is also used as an excellent absorbent in carbon dioxide. Cesium is used in devising photoelectric cells. General characteristics of the compound of the alkali metals. All the common compounds of the alkali metals are generally ionic in nature. General characteristics of some of the compounds are discussed here. The oxides and hydroxides and combustion in excess of air. Lithium forms mainly the oxide Li2O plus some peroxide Li2O2. Sodium forms the peroxide N2O2 and the some superoxides NaO2, while potassium, rubidium, and cesium form superoxides MO2 under appropriate conditions. Pure compounds M2O, M2O2, and MO2 may be prepared, and the increasing stability of the peroxide or superoxide as the size of the metal ion increases is due to the stabilization of large anions by larger cations through lattice energy effects. These oxides are easily hydrolyzed by water to form the hydroxides. According to the following reactions, M2O plus H2O then gives 2 times M positive plus 2 times OH negative. M2O2 plus 2 times H2O then gives 2 times M positive plus 2 times OH negative plus H2O2. 2 times MO2 plus 2 times H2O, and then gives 2 times M positive plus 2 times OH negative plus O3H2O2 plus O2. The oxides and the peroxides are colorless when pure, but the peroxides are yellow or orange in color. The superoxides are also paramagnetic. Sodium peroxide is widely used as an oxidizing agent in organic chemistry. Problem 10.3. Why is KO2 paramagnetic? The superoxide O2 negative is paramagnetic because of one unpaired electron in a pi 2p molecular orbital. The hydroxides, which are orbital by the reaction of the hydroxides which with the water, are all white crystalline solids. The alkali metal hydroxides are the strongest of all bases and dissolve freely in water. With the evolution of such much heat on account of intense hydration, halides the alkali metal halides MXFL, fluorine, chlorine, bromine, iodine are all high melting colorless crystalline solids. They can be prepared by the reaction of the appropriate oxide, hydroxide, and carbonate with aqueous hydraulic acid. All of these halides have high negative enthalpies of formation of the H delta H values of for fluorides now become less negative as we go down the group. Bromides and iodides for a given metal delta of H always becomes less negative from fluoride and iodide. The melting and boiling points always follow the trend fluoride, chloride, bromide, iodide. All these halides are soluble in water. The low solubility of CalI in water is due to its high lattice enthalpy, whereas the low solubility of cesium SCl is due to the smaller hydration enthalpy of its two ions. Other halides of lithium are soluble in ethanol, acetone, and ethyl acetate. LiCl is soluble in pyridine also. Salts of oxoacids. Oxoacids are those in which the acidic proton is on the hydroxyl group with an oxo group. Mm, Oxo group attached to the same atom. Example carbonic acid H2CO3 on OCOH2 times sulfuric acid H2SO4 O2OH2 times. The alkali metals form salts with all the oxoacids. They are generally soluble in water and they are thermally stable. Their carbonates M2O3 CO3, and in most cases the hydrocarbonates MH on CO3 also are highly stable to heat as the electropositive character increases down the group. The stability of the carbonate and hydrogeneration carbon carbonates increases. Lithium carbonate is not so stable, so to heat. Lithium, being very small in size, polarizes of large CO3 negative ion, leading to the formation of more stable Li2O and CO2. Its hydrogen carbonate does not exist as a solid. Anomalous properties of lithium. The anomalous behavior of lithium is due to the first exceptionally small size of its atom ion, second high polarizing power, that is charge per radius ratio. As a result, there is an increased covalent character of lithium compounds which were responsible for their solubility in organic solvents. Further, lithium shows diagonal relationship to magnesium, which has been discussed subsequently. Point of difference between lithium and other alkali metals. Lithium is much harder. Its melting point and boiling point are higher than the other alkali metals. Lithium is very least reactive but the strongest reducing agent among all the alkali metals. On combustion in air, it forms mainly monoxide Li2O and the nitride Li3N. Unlike other alkali metals, LiCl is deliquescent and crystallizes as hydrate LiCl 2.2 times H2O, whereas other alkali metal chlorides do not form hydrates. Lithium hydrogen carbonate is not obtained in the solid form, while all the other elements are form solid hydrogen carbonates. Lithium, unlike other alkali metals, forms no ethanide on a reaction with the ethine. Lithium nitrate, when heated, gives lithium oxide Li2O, whereas other alkali metals nitrates decompose to give the corresponding nitrite. LiF and Li2O are comparatively much less soluble in water than the corresponding compounds of other alkali metals. So points of similarities between lithium and magnesium. The similarity between lithium and magnesium is particularly striking and arises because of their similar sizes. Atomic radii: lithium is equal to 152 pm, magnesium is equal to 160 pm. Um, Antigradial lithium Li positive is equal to 76 pm, Mg positive is equal to 72 pm. Now, the main points of similarity are both lithium and magnesium are harder and lighter than other elements in the respective groups. Lithium and magnesium react slowly with water. Their oxides and hydroxides are much less soluble, and their hydroxides decompose on heating. Both form the nitride Li3N and Mg3N2 by direct combination with nitrogen. The oxides Li2O and MgO do not combine with excess oxygen to give any superoxide. The carbonates of lithium and magnesium decompose easily on heating to form the oxides and CO2. Solid hydrogen carbonates are not formed by lithium and magnesium. Both lithium, LiCl and MgCl2 are soluble in ethanol. Both LiCl and MgCl2 are deliquescent and crystalline from aqueous solution as hydrates. LiCl dot 2 times H2O and MgCl2 will dot 8 times H2O. Some important compounds of sodium. Industrially important compounds of sodium include sodium carbonate, sodium hydroxide, sodium chloride, sodium bicarbonate, and the large scale production of these compounds and their uses are described below. Sodium carbonate, washing soda, Na2CO3 dot 10 times H2O. Sodium carbonate is generally prepared to solve process. Now, in this process, the advantage of is taken of the low solubility of sodium hydrogen carbonate, whereby it gets precipitated in the reaction of sodium chloride with ammonium hydrogen carbonate, and the latter is prepared by passing CO2 to a concentrated solution of sodium chloride saturated with ammonia, where ammonium carbonate followed by ammonium hydrogen carbonate are formed. The equations for the complete process may be written as 2 times NH3 plus 2 H2O plus CO2 then gives NH4 2 times CO3, NH4 2 times CO2 plus H2O plus CO2 then gives 2 times NH4 H CO2 CO3 NH4 CO3 plus NaCl then gives NH4Cl plus NaHCO3 sodium hydrogen carbonate crystal separates, and these are heated to give sodium bicarbonate Na 2 times NaCO3 then goes to Na2CO3 plus CO2 plus H2. In this process NH2 is recovered when the solid solution containing NH4Cl is treated with CaOH 2 times calcium chloride is obtained as a byproduct 2 times NH4Cl plus CaOH 2 times then gives 2 times NH3 plus CaCl2 plus H2O. It may be mentioned here that solvent process cannot be extended to the manufacture of potassium carbonate because potassium hydrogen carbonate is too soluble to be precipitated by the addition of ammonium hydrogen carbon to a saturated solution of potassium chloride. Properties: sodium carbonate is a white crystalline solid which exists as a decarhydrate Na2CO3 dot to 10 times H2O. This is also called a washing soda, and it is readily soluble in water on heating. Now the dehydrate losses its water and of crystallization to form monohydrate above 373 Kelvin. And the form of monohydrate becomes so completely anhydrous. The changes to a white powder called soda ash. Na2CO3 plus 10 and dot 10 times H2O, and then gives to Na2CO3 dot H2O plus 9 times H2O. Na2CO3 dot H2O then gives Na2CO3 plus H2O. The carbohydrate part of sodium carbohydrate gets hydrolyzed by water to form an alkaline solution CO3 negative plus H2O then gives CHCO3 negative plus OH negative. It is used in water softening for laundering and cleaning. It is used in the manufacture of glass, soap, borax and caustic soda. It is used in paper, paints and texture industries. It is an important laboratory reagent both in qualitative and quantitative analysis. Sodium chloride NaCl. The most abundant source of sodium chloride is seawater, which contains 2.7 to 2.9 percent by the mass of the salt. The tropical countries like India, common salt is generally obtained by evaporation of seawater. Approximately 50 lakh ions of salt are produced annually in India by solar evaporation. Crude sodium chloride, generally obtained by crystallization of brine solution, contains sodium sulfate, calcium sulfate, calcium chloride, and magnesium chloride as impurities. Calcium chloride LCaCl2 and magnesium chloride MgCl2 are impurities because they are delicate, absorb moisture easily from the atmosphere to obtain pure sodium chloride. The crude salt is dissolved in minimum amount of water and filtered to remove insoluble impurities. The solution of the is then saturated with the hydrogen chloride gas. Crystals of pure sodium chloride separate out. Calcium and magnesium chloride being more soluble than sodium chloride remain insoluble remain in solution. Sodium chloride melts at 1081 Kelvin. It has a solubility of 36 gram in 100 gram of water at 273 Kelvin. The solubility does not increase precisely. Now, appreciably with increase in temperature. It is used as a common salt and table salt for domestic purpose. It is used for the preparation of Na2O2 and NaOH and Na2CO3. Sodium hydroxide, caustic soda, NaOH. Sodium hydroxide is generally prepared commercially by the electrolysis of sodium solution. Sodium chloride in custard cleaner cell. A brand solution is electrolyzed using a mercury cathode and a carbon anode. A sodium metal discharged at the cathode combines with the mercury to form sodium amalgam. Chloride gases evolve at the anode. The sodium positive plus electron then gives sodium amalgam. The amalgam is treated with water to give sodium hydrates and hydrogen gas. So it's two times Na amalgam plus two times H2O then gives two times NaOH plus two times Hg plus H2. Now sodium hydroxide is a white translucent solid. It melts at 291 Kelvin. It is readily soluble in water to give strong alkaline solutions. Crystals of sodium hydroxide are deliquescent and the sodium hydroxide solution at the surface reacts with the CO2 in the atmosphere to form Na2CO3. It is used in the manufacture of soap and artificial silk and the number of chemicals in the petroleum refining and the purification of bauxite and the textile industries for mercerizing cotton fabrics for the preparation of pure fats and oils as laboratory reagent. Sodium hydrocarbonate, baking soda, and HCO3. Sodium hydrogen carbonate is known as baking soda because it decomposes on heating to generate bubbles of carbon dioxide, leaving holes in cakes or pastries and making them light and fluffy. The hydrogen carbonate is made by saturating the sodium and sodium carbonate with carbon dioxide. The white crystalline powder of sodium hydrogen carbonate, being less soluble, gets separated out Na2CO3 plus H2O plus CO2, then gives 2 times NaHCO3. Sodium hydrogen carbonate is a mild antiseptic for skin infections. It is used in fire extinguishers. Biological importance of sodium and potassium. A typical for 70 kilogram man contains about 90 kilogram of sodium and 170 gram of 170 gram of potassium compared with only 5 gram of iron and 0.06 gram of copper. Sodium ions are found primarily on the outside of cells, being located in blood plasma and in the intestinal fluid which surrounds the cells. These ions participate in the transmission of nerve signals and regulating the flow of water across cell membranes and in the transport of sugars and amino acids and to cells chemically differ quantitatively in their ability mechanisms and their efficiency to activate enzymes. Thus potassium ions are the most activate many enzymes. Potassium ions are most abundant cations within cell fluids where they are activate many enzymes participate in the oxidation of glucose and to produce ATP and with sodium are responsible for the transmission of nerve signals. And there is a very considerable variation in the concentration of sodium and potassium ions found on the opposite sides of cell membranes. As a typical example in blood plasma, sodium is present on the to the extent of 143 millimeter of per liquid, whereas the potassium level is only 5 millimeter of per liquid. within the red blood cells. This concentration change to 10 millimeter of per liquid per liter for sodium, and on 105 millimeter per liter potassium. These ionic gradients demonstrating that a discriminatory mechanism called as the sodium potassium pump operates across the cell membranes, which as consumes more than one third of the ATP used by the resting animal, and about 15 kilogram per 24 hour in the resting human. Group 2 elements, alkaline earth metals. The group 2 elements comprise beryllium, magnesium, calcium, strontium, barium, and radium, and they follow alkali metals in the periodic table. These, except beryllium, are known as alkaline earth metals. The first element, beryllium, differs from the rest of the members of the and shows a diagonal relationship to the aluminium. The atomic and physical properties of the alkaline earth metals are shown in table 10.2. Electronic configuration. These elements have two electrons in the s orbitals of the valence shell. Table 10.2. Their general electronic configuration may be represented as noble gas NS2. Like alkali metals, the compounds of these elements are also predominantly ionic. Atomic and ionic radii. The atomic and ionic radii of the alkaline earth metals are smaller than those of the corresponding alkali metals in the same periods. This is due to the increased nuclear charge in these elements within the group. The atomic and ionic radii increase with increase the atomic number. Ionization enthalpies. The alkaline earth metals have low ionization enthalpies due to fairly large size of the atoms. Since the atomic size increases down the group, their ionization enthalpy decreases. Now, the first ionization enthalpies of the alkaline earth metals are highly higher than those of the corresponding groups of 1 metals. This is due to their small size as compared to the corresponding alkali metals. Now, it is interesting to note that the second ionization enthalpies of the alkaline earth metals are smaller than those of the corresponding alkali metals. Hydration enthalpies. Like alkali metal ions, the hydration enthalpies of alkaline earth metals ions decreases with increasing in ionic size. Shown the group, beryllium is greater than magnesium is greater than calcium is greater than sodium is greater than beryllium. The hydration enthalpies of alkaline earth metals ions are higher, larger than those of alkaline metal science. Thus, compounds of alkaline earth metals are more extensively hydrated than those of the alkaline metals. An example, MgCl2 and CaCl2 exists as MgCl2 so dot 6 times CH2O and CaCl2 plus dot 6 times CH2O, while NaCl and KCl do not form such hydrates. Physical properties. The alkaline earth metals in general are silvery white, lustrous, and relatively soft but harder than the alkali metals. Beryllium and magnesium appear to be somewhat grayish. The melting and boiling points of these metals are higher than the corresponding alkali metals due to smaller sizes. The trend is however not systemic because of the low ionization enthalpies. They are strongly electropositive in nature. The electropositive character increases down the group from beryllium to barium, calcium, strontium, and barium impart characteristic of brick red, crimson, and apple green colors, respectively, to the flame. Now, in flame, the electrons are excited to higher energy levels, and when they drop back to the ground state, energy is emitted in the form of visible light. The electrons are in beryllium and magnesium are too strongly bound to get excited by flame. Hence, these elements do not impart any color to the flame. The flame taste of or calcium Chemical properties: reactivity towards air and water, reactivity towards the halogens, reactivity towards hydrogen, reactivity towards acids, reducing nature, solutions in liquid ammonia, uses. General characteristics of compounds of the alkaline earth metals, oxides and hydroxides, halides, salts and oxoacids, carbonates, sulfates, nitrates. Anomalous behavior of beryllium, diagonal relationship between beryllium and aluminium. Some important compounds of calcium, calcium oxide or quicklime, CO uses, calcium hydroxide, slacked lime, COOH 2 times uses, calcium carbonate, CaCO3 uses, calcium sulfate, plaster of Paris, CaCO3 dot half times H2O uses, cement, setting of cement uses, biological importance of magnesium and calcium. Then summary, this block की summary. The S block of the periodic table constitutes group 1 alkali metals and group 2 alkaline earth metals. They are so called because their oxides and hydroxides are alkaline earth in nature. The alkali metals are characterized by one S electron and the alkaline earth metals by two S electrons in the valence shell of their atoms. These are highly reactive metals forming monopositive M positive and I positive M dipositive ions respectively. There is a regular trend in the physical and chemical properties of the alkali metal with increasing atomic numbers. The atomic and ionic sizes increase and the ionization enthalpy decrease systematically down the group. Somewhat similar trends are observed among the properties of the alkaline earth metals. The first element in each of these groups, lithium in group 1 and beryllium in group 2, shows similarities in properties or to the second member of the next group. Now, such similarities are termed as the diagonal relationship in the periodic table. As such, these elements are anomalous as far as their group characteristics are concerned. The alkali metals are silvery white, soft and low melting. They are highly reactive. The compounds of alkali metals are predominantly ionic. Their oxides and hydroxides are soluble in water, forming strong alkalis. Important compounds of sodium includes sodium carbonate, sodium chloride, sodium hydroxide, sodium hydrogen carbonate. Sodium hydroxide is manufactured by castor cleaner process and sodium carbonate by Solvay process. The chemistry of alkaline earth metals is very much like that of the alkali metals. However, some differences arise because of reduced atomic and ionic sizes and increased cationic charges. In case of the alkaline earth metals, their oxides and hydroxides are less basic than the alkali metal oxides and hydroxides. Industrially important compounds of the calcium include calcium oxide, lime, calcium hydroxide, slaked lime, calcium sulfate, plaster of Paris, calcium carbonate, limestone, and cement. Portland cement is an important constructional material. Now it is manufactured by heating the pulverized mixture of limestone and clay in a rotary kiln. The clinker thus obtained is mixed with some gypsum and 2 to 3% to give a fine powder of cement. All these substances are variety of uses in different areas. Monovalent sodium and potassium ions and divalent monomagnesium and calcium ions are found in large properties in biological fluids. These ions perform important biological functions such as maintenance of ions and balance and nerve impulse conduction. तो ये कुछ इस ब्लॉग के इम्पोर्टेंट समरी थी और ये कुछ इम्पोर्टेंट टॉपिक्स एंड पॉइंट्स थे इस ब्लॉक एलिमेंट्स के। इस ब्लॉक के एलिमेंट्स यहाँ पर ख़त्म होता है जहाँ पर हमने पहले से देखा ग्रुप 1 एलिमेंट्स, सर्कल लिमिटर्स, इलेक्ट्रॉनिक कॉन्फिगरेशन, एटॉमिक एंड आयनिक रेडिया, आयनाइजेशन एंथैल्पी, हाइड्रेशन एंथैल्पी, देन फिजिकल प्रॉपर्टीज, देन केमिकल प्रॉपर्टीज, देन उसके बाद हमने देखा यूजेस, देन उसके बाद हमने देखा जनरल कैरेक्टरिस्टिक्स ऑफ द कंपाउंड्स ऑफ द alkali metals, oxides and hydroxides, halides, salts and oxoacids. Now, anomalous properties of lithium, points of difference between lithium and other alkali metals, Points of similarities between lithium and magnesium. Some important compounds of sodium. Sodium carbonate, washing soda, uses sodium chloride. NaCl uses sodium hydroxide. Caustic soda, NaOH. Sodium hydrocarbonate, carbonates, baking soda, NaHCO3. Biological importance of sodium and potassium. Group 2 elements of alkaline earth metals. Electronic configuration, atomic and ionic radii. Ionization enthalpy, hydration enthalpy. Physical properties, chemical properties. Uses, general characteristics of compounds of the alkaline earth metals. Anomalous behavior of beryllium, diagonal relationship between beryllium and aluminium. Some important compounds of calcium. Uses, calcium hydroxide, like lime, CaOH 2 times. Now uses, calcium carbonate, CaCO3. Uses, calcium sulfate, plaster of Paris, CaSO4, dot half H2O. Uses, cement, setting of cement. Uses, बायोलॉजिकल इंपॉर्टेंस ऑफ मैग्नीशियम एंड कैल्शियम, देन समरी। तो यहाँ पर हमारा ये ब्लॉक चैप्टर ख़त्म होता है। प्लीज़ इस वीडियो को ज़्यादा से ज़्यादा शेयर कीजिएगा। प्लीज़ लाइक शेयर एंड सब्सक्राइब। थैंक यू सो मच फॉर वॉचिंग।